Oh, okay. Hello. So let's wait for a few minutes, and then we can start. Today's questions will be on cascode-based circuits, and you will get to know how we can draw the equivalent circuits for cascodes and how we can obtain small signal parameters such as gain, output resistance, capacitances, frequency response. Okay, so let's wait for 10 minutes so we can start. Okay, so we can start. So as I said, the session is related to week 8, which was focused on cascode-based amplifiers. And now we will do some questions related to it. So if you happen to see the video and you have some doubts or what I can say, and you need to know the correct answers because I won't solve every question here. No, I won't find the final answers. So you can always comment in the videos. So let's start. Let's read the question first. These are two transistors, Q1 and Q2. Mm, VB1, VB on, 1 second. Okay. VB on for the both transistors is given equivalent to 0.6, 0.6 volt. And these are the saturation voltages for VCE. First things first, it is a NPN transistor. The positive bias is applied on this terminal, so this is collector, this is emitter, and this is the collector for Q1, and this is the emitter for Q1. This is base. Okay. Also, beta 1 and beta 2 are given. Beta 1 is 120, that is for Q1, and we have beta 2 equal to 240, that is for Q2. Also, early voltages are given. 120. Source resistance is 1.73 kilo. Okay, this is thermal equivalent. The values of components in the amplifier are given to the, and these are the values of the resistances. I'm not writing this. And also, yeah, so we have also C pi and C mu given. Supply voltage is 12 volt. Okay, and I bias is given to us as 1.8 milliampere. And now what we have to find is small signal output resistance in the amplifier. First, if you happen to see the video, pause the video and draw the equivalent circuit by yourself and then try to get the small signal output resistance. Now I will start doing this session. I will start by drawing the equivalent circuit. Let me just one second. let me just draw the circle. This is what Q1. Let's first draw for Q1. Okay, let me just start from the bottom so we can draw then for Q2 as well. So it will start with V in, then we have series distance. Let's assume the capacitance are all shorted. So we'll just have, see here, R1, and we will ground this VCC. So we will have R1 here, right? And then what we have? R5, and we have emitter, which is the grounded, which is base, and we will have GM, VBE, let's call it 1, 1. And we will have it, because VA1 is given, so we will have a resistance as well. This is your collector. Now say, this is for Q1. You see, collector and emitter are same for Q2. So we can write here, this is the emitter for second transistor, right? So this will be its GM2. Let's call it VBE2. So it will be, let's call it R pi 1, R pi 2. Oh, there is R2 and R4 are in parallel. We will have R2 parallel R4. And this has to be grounded because there is no supply. This is DC supply, so it will be grounded. Alright. And we will have R2, and at the output we have R3. Right. This is your output. Is this alright? So I hope this is easy to draw. This is the equivalent circuit. Now what we have to find is output resistance. Right. So what we will do is we will attach a test source here. Vx, Ix. And then after we find a equivalent resistance, looking into collector of Q2, let's say, right, let me write it. We'll find an equivalent resistance at node V out by looking into, or you can write at collector or node collector. So I'm writing here looking into collector of transistor Q2. So we will find our equivalent. Then what we will do is to find the total output resistance. we'll write R out is equivalent to R equivalent parallel to R. Okay, right? So let's just start. Okay, so let's start from this node. We attach it, we X to it, and let's call this terminal V1. Okay, so let's start a nodal analysis. ACL at node layout. So we have attached Vx to it, so it will be at a potential of Vx, right? So if we just start with KCL, so this will be Vx minus V1 by R of 2, right? This is at Vx, this is at V1. So it will be Vx minus V1 by R of 2 plus current flowing through Q2 is Gm Vb E2, right? And it will be equivalent to the current going into the node, that is Ix, right? Now let's see, we have V1 that is related to Q1. Let's first see what is VBE2. VBE2 is attached to ground, so and E is V1, so VBE2 is VB minus V1, that is minus times V1. So Vx by R02 minus V1 by R02 minus Gm V1 is equivalent to Ix. So now the second part in this question would be to find V1, right? So now look here for V1. Let's make an equivalent circuit for to find the V1. See here, this is grounded. So this terminal is grounded, this terminal is grounded, so there is no effect of this resistance. And here it will be grounded. So what I can do is, this will be also grounded. So when this is grounded, so this will be R1 parallel RS, but this is at, okay, this will be grounded. This node potential is 0, this will be 0, and this will be 0. So I can write, so let me just draw. So what will remain is, this is R phi 2, and this is grounded, and this is R01, and this will be open because this is 0, and this will be grounded. And because B is at node 0, so this will be at 0 potential. This is open. So this is my V1. So what will be it will be? So this will be a resistance of R of 1 parallel to R pi 2. So the current Ix here will come, and this will be my Ix. It will flow through a parallel combination of R pi 2 and R01. So my V1, can I write it as Ix RO1 parallel to R pi 2, right? So now substitute it here. So what we will get is, first let's simplify the expression. Vx2 is equivalent to V1 1 by R of 2 plus Gm plus Ix. Okay, so this is Vx by R of 2 is equivalent to Ix R of 1 parallel R pi 2 1 by 1 by RO 2 plus Gm, one second, plus Ix. Okay, okay, this Gm is Gm2. So Vx by R of 2 will be equivalent to Ix times R of 1 parallel R of R pi 2 plus R of 2 plus Gm2. So my R out, let's call it R equivalent, will be Vx by Ix, and that will come out to be R of 2 multiplied by R of 1 parallel R pi 2 plus 1 by R of 2 plus Gm2. That is R equivalent will be R of 2 R of 1 parallel R pi 2 plus Gm2 R of 2 plus 1. So this is your equivalent resistance. And now total output resistance will be given by, yes, R equivalent parallel R3. Okay, so this is your total R out. So now there are different parameters, resistances, which are unknown right now. So we need to calculate these, right? So calculations. So we need to find RO2, RO1, R pi 2, GM2, and R3 is given to us. So let's see. We know R of 1 will be equivalent to VA1 by IC1. R pi be beta 1 by GM1. Similarly, R pi 2 will be beta 2 by GM2. And my GM1 will be IC by VT. Similarly, GM2 will be IC2 by VT. Now note that if we have transistors in series, then same current flows through the connected transistors, right? So if I have transistors here, so if a current of 1 milliampere flows through it, then also through this transistor, current of 1 milliampere flows. So you cannot just generate if you have a single two nodes and there will be a constant current. You cannot have zero point 0.5 from this node to this node, and then yeah, if you have another terminal here connected, then it's okay. But if you have single line, single transistor, there is no sources, then you have same currents. So here also we have transistors in series, so IC1 will be equivalent to IC2. What this will mean is, if you look at the expressions for GM1 and GM2, then GM1 will be equivalent to GM2. And also we have, let's go back, VA1 and VA2 are equivalent. So our RO1 will be equal to RO2 as well. Only different will be R pi 1 and R pi 2 because beta are different. So let's just have some calculations. I see one second. Okay, now also uh, we have, okay, where is it? Hmm. Okay, so if you see the circuit, now if you want to find this base current, it's easy, right? From this point of view, it will be difficult because there are different paths. There is a path through R4 as well. But here you can see there is a capacitor, DC block. So if a current comes in this loop, so all the current will flow through here. So this will be treated as a base current. Now look here, VBE1 is given to us as 0.6. So can I write as IB1 is equivalent to VCC across this R1 minus VBE is given to us as 0.6 divided by R1, right? So this will be IB1 will be 12 minus 0.6 by R1. R1 is 760 kilo ohm. So see, when you calculate it, IB1 comes out to be 15 microampere. Now note that, right? IB1 is equivalent to 15 microampere. Now can I calculate IC1 and IC2? IC1, that will be beta 1 times IB1. Beta 1 is 120, right? Beta 1 is 120. Yes. Comes out to be 1.8 milliampere. So this is your collector current. Now, there is an easy way also to see the value of current. See here, the transistors are biased using a current source. So, current source is given to us as 1.8 milliampere. So that means this collector has a 1.8 milliampere current. So this is the amount of current that should flow through the collector terminal. So we could have directly written this value, and since R3 is very high, so I bias will be equivalent to I collector. So we could have directly written it, so it's okay. We found the same answer, so we have calculations are correct. So now that we have IC1, so IC2 will be IC equivalent to IC1, 1.2. Alright, so let's calculate. Okay, GM1, as I said, will be equivalent to GM2. That will be given by IC divided by VT. Let's now write these values as IC. So this will be milliampere, VT, no, first 96 millivolt, will be given by 0.069, or we can write it as a fraction 9 divided by 1, 30 Siemens. The next is we have to calculate R pi 1, that is beta 1 by GM1. Beta 1 is 120, GM1 is 9 into 130. This will be equivalent to 120 into 130 divided by 9. Okay, comes out to be equivalent to 1733.33. Okay, so we have R by 2 is equivalent to beta 2 by GM2, that is 240 divided by GM2 is again 9 into 130. That should be 2 times the previous answer. 240 divided by 9. That is 3466.66. Now we have R pi 1, we have G1, R pi 1. Now we are left with R of 1, that's equivalent to R of 2 because earlier voltage are same. So this will be VA by IC. VA is 120, IC is 1.8 milli. So it will be 120 divided by 1.8. That comes out to be 66.66 kilo ohm. Right? So now we have all the values. Now what we have to do is do it as an exercise. Substitute the values in R equivalent, and you know the R3 as well. R3 is given to us as 10 mega ohm. So solve the question, solve it for R equivalent, then solve it for R out. You should get an answer of around 6.04 mega ohm. Yes. All right. Now that we are done with this first part, we can move to second one. And also, let me just write the answer for our equivalent. Comes out to be 15 mega ohm. Find the values. If these values are incorrect, please do comment in the video. Okay. Now let's move to the second question. Find the DC. Find the DC voltage. That is V out. V out is V out is here. We have to find this voltage V out between collector Q2 and ground terminals first. Okay. Hmm. So now we calculated R out, and as I said, it is 6.04 mega ohm. But we calculated R equivalent as well, 15 mega ohm. Now let me just draw. This is your Q2, right? Forget about it. What is on this side? Just look here. This is your R3. This is your VCC. That is 12 volt. Now you know calculated the resistance here. That is from this node to the ground, and that is R equivalent is equal to 15 mega ohm, and R3 is given to us as 10 mega ohm. Now can you see we have VCC 10 mega ohm, and then we have another resistance that is R equivalent equal to 15 mega ohm. Now we have to find this voltage. So it will be V out is equivalent to 15 mega ohm, nearly equal to. There may be some other terms, but this is a very quick way to answer the question. So we can directly write 15 mega ohm plus 10 mega ohm. That is VCC. Right. That is 15 divided by 25 into 10. That comes out to be V out 7.2 volt. Alright. This is the easiest. We find it easy because we already calculated R equivalent. For practice purpose, repeat the exercise for this part as well, and you will then find it easy to do. Next, what we have to calculate is gain. Okay, so this is another good question because it will involve this equivalent circuit again. Let me see if I can copy this circuit. Let me just so we have to find gain, so we need input as well. So okay, so this is your equivalent circuit. Just cross check it. Hmm, right. Now we have to find the output by V in. So let's first see how we can relate this node V1 with V output, then we will find, or what we can do is we'll first find V1 in terms of V in any case it's both are equal to uh, equal approach. Let's first see then what is V out. Let's do a node analysis here. So we will have V output by R3 plus this is V output minus this is V1 by R2 plus GM VBE2 equivalent to 0. Now again VBE2 is equal to VB minus V1 and this will be V1 because VB is at 0 to 0 voltage. So my V output is So I can write V output 1 by R3 plus 1 by R naught is equivalent to by R plus R3 RO2 divided by RO2 plus R3 1 plus GM2 RO2 divided by RO2 RO2 go. So my V output is equivalent to R3 divided by RO2 plus R3 1 plus GM2 102 V1. This is my V output in terms of V1. Now what next? We have to calculate V1. One second. Okay, so let's again go to our circuit. So how we can find V1? This is a V1. So this will be an output from transistor Q1. So what we need to do is we need to find R looking into the emitter of Q1. So we need to find REQ1, right? Then we will have equivalent resistance from this part, upper part, and that will be in parallel to RO1. So then we can write V1 as GM1 maybe E1 multiplied by R. This R will be R equivalent R emitter Q1 parallel to R by 2 parallel to R01. So we are assuming here that R equivalent emitter Q1 from this portion, and then that will be in parallel combination to R by 2. So let's just start with finding REQ1. I just draw this. So if we apply the KCL at this node, KCL, we will have Ix going in, GMVBE 2, and we will have current, let's say Vx minus, this is V out, Vx minus V out followed by RO2, right? So if this is a current of Ix, so there has to be current of Ix here, so my V output will be Ix times R3. So this will be Ix, and again VBE to B is at a potential of, this is grounded, right? This is R pi 2. So VB E2 is VB minus Vx here. This time this is x, so this will be minus Vx. So this will be G of Vx by R02 minus Ix R3, right? So let's just calculate it. Ix will be 1 plus R3, and Vx will be 1 by R02. This will be 1 plus Gm2. Maybe x by Ix will be R02 1 plus R3 divided by 1 plus Gm2 R02. Is this correct? Yes, it is correct. So we found this resistance. Now total, our total looking into emitter of Q2 will be R pi 2 parallel to R equivalent Q2, right? Not solving this, please do it yourself. So now my gain for gain from transistor Q1 will be minus Q1. It will be like this, right? Just draw the output here. Fine. Now, one second. The question says you have to take RS as well. So the gain we calculated is this is V1 divided by VBE1, and that is GM1 R01 parallel to R52 parallel to R equivalent or emitter equivalent to. So my VBE1 is again equivalent to R51 divided by RS plus R51 into V in. Once you find the value, you have found the values of R51 and R52. Yes, I guess yes. You have found these values, so you can directly use these values and find this VBE in terms of V in. So my V1 by V in will be equal to minus GM1. Let me just write it out in parallel. Our total equivalent to Q2 into R by 1 divided by RS plus R by 1. This is my V1 in terms of V in. Now what we have to do is we have to find V output in terms of V in. let's just go back. We have the expression for R V out. Let me just write it. R3 by R naught. Correct. And now we have this expression as well. V1 is equivalent to minus G1. Let me just substitute it here. So my V out will be R3 by R naught rho. That is R3 1 plus G into R naught rho to V1. That is G1 R naught 1 parallel R EQ1 R pi 1 divided by R pi 1 plus RS. So this is my total gain. Please do substitute the values and post the answers. All right. Okay. Was there anything else in this? Okay. Next is finding the capacitance. Just the part of the circuit. This is my input. Input is related to Q1, right? This is my R naught 1. This is my R pi 2. This is my R emitter equivalent circuit 2. This will be RS. This will be your, right? This is how your equivalent circuit will look. So we use the equivalent resistances. Now I have just drawn these two capacitances because we have to find the input capacitance. So we know from Miller's theorem, C input effective will be the C pi plus C mu times 1 minus AV. Here AV is gain of Q1, right? So we have used, we found in previous part that gain is simply equivalent to minus GM R naught 1 parallel to R pi 2 parallel to Q2. So here we don't, so RS is not mentioned, so RS is ignored here, so we will have this gain. Let me just we know these values, right? You just have to calculate this equivalent uh, resistance. So you will get an answer of 90.5. Now, if you substitute it, C input effective will be, what is C pi? C pi is 10 pico, C mu is 5 pico, 10 pico and 5 pico. Solve this and we'll get an answer of 467 picofarad. Let me just cross check. Yes. So this is the answer for your input capacitance. Now, following the part, we have to calculate the cutoff frequencies. So, as I said, uh, lower cutoff, look for input capacitance. Upper cutoff, look for input effective capacitance. If see your elastic capacitance are given, and again for upper cutoff, output capacitance. Now we have to find the upper cutoff frequency. I can just directly write it as 2 pi uh, C in effective calculated previously. Let's just look at your circuit. So this is your R1 as well. If I have to find frequency corresponding to this capacitance, so I will look for the resistance here R in. So if I had to ground this VIN, short this VIN as well, so it will be RS parallel R pi, RS parallel R1 parallel R pi, right? So my resistance here component will be RS parallel R1 parallel R pi 1, right? Similarly, output will be given by just okay. So it will be given by this output capacitance and total R, right? R out, which I guess we have in our hand. Mhm. Right, this 6.04 mega ohm. So you can just directly write it as 1 divided by 2 pi CL R out. So you now know this is the value of 6.04 mega ohm. CL is given to you. Substitute the values, you know every value. So you will get a 1394 kilohertz, and for this you will get a value of 264 64 kilohertz. So One second. Let me just cross check the value. This will be 1 by 2 pi into CL is 100 pico, and this is your 6.04 into 10 raised power 6. So this will be 10 raised power, okay, minus 6, minus 4. This will be 2 pi into 6. That will be 1000 divided by 2 divided by 3.14 divided by 6. That's correct. So this is 265.4 hertz. So this will be your upper cutoff because it is the minimum of the two, right? Okay, so questions related to BGT are done. So let's do one or two questions on MOSFET. Give it a read. Give this question a read. I will just take 2 minutes rest. Okay, so this is a MOSFET based question. Again, these are MOSFETs in series, but be assured that this is PMOS and this is your NMOS, right? So values are given, your channel negative modulation parameters are also given. We have to find the DC gate voltage of transistor M2. We have to find this gate voltage, VG. Says that find the DC gate voltage of transistor. Assume the meaning of I to get is okay. So again, there is a concept that the current flowing through M2 will be equal to current flowing through M1. So we have to use this. So let's see first what is VG1. VG1 is simply R2 divided by R1 plus R2 into VDD, right? So my R2 is given to us as 30 kilo ohm divided by R1 plus R2, that is 90 kilo ohm plus 30 kilo ohm into VDD, that is 12. That is 3 volt. Now you know VG1 is 3 volt. Can you just tell me what the idea is? Yes. If we treat it as an saturation, it will be 2L VGS minus VTH whole square, right? So let me just see the values. It is 0.5 for NMOS. It will be 0.5 milli by 2. So this is 3 minus 1 whole square. That will be 0.5 milli into 4 divided by 2. This will give me current of 1 milliampere, right? So this 1 milliampere current, as I said, it will flow through the M2 as well, right? Let me just write the equation for M2. That will be ISD is equivalent to Kw by 2L VSG minus VTHP whole square, right? So ISD is 1 milliampere. Kw by L is 2 milli given to us. 2 milli by 2. VSG is Vs minus Vg2 minus VTH. VTH is given to us as minus 1, so it will be 1 whole square. And my Vs is equivalent to VDD, that is 12. So milli and milli will go. My Vs minus Vg2 minus 1 will be equal to plus minus 1. My Vs is 12, 12 minus 1 is 11, minus Vg2 will be plus minus 1 minus times 11. So my Vg minus Vg2 will be equivalent to two values, minus 12, that is 12 volt, or my Vg2 will be, if it is plus 1, it will be minus 10, that will give me 10 volt. So these are two values. So if I use 12 volt, then my VSG will be 0, transistor is off, so not possible, so 10 volt is the correct one. So this is 10 volt. So this is what we have to find. Moving on, next question has, it is related to R4. We have to find the value of R4 such that the same current flowing between transformers. Okay, again have to do this concept. IDS is equal to IST. All right. Okay. Uh, R4. Right. So here we have to take into account of the output as well. So we will take the whole expression, that is IDS will be equal to Kw by 2L VGS minus VTH whole square into 1 plus lambda 1 times V out, right? Because it will be VDS. So VDS for this transistor is V out, right? And it will be equivalent to IST, that is again given by QL VSG minus VTHP whole square. And again, for this transistor, it will be lambda 2 times VDS2. And for this transistor, this is source, this is drain. VDS2 will be equivalent to I have to write it as, sorry, VST. It's not VDS, it's VST2. So my VST2 will be equal to 12 minus V out. So these are equal, so let me just equate it. That will give me KW by 2L. These are different for different. Let me write it as N, let me write it as P. So N VGS is again given to us as 3 minus 1, that is 2, 2 is power to 4. 1 plus lambda 1 times V out is equivalent to KW by 2L. P VSG is again given, that is 12 minus 1. No, sorry, VSG is VSG2 is 12 minus 10, that is 2. 2 minus 1 is 1, 1. That will give me 1. 1 plus lambda 2 times 12 minus V out. Okay, so you know these values, so you solve the question and you will get an output voltage of 7.2 volt. Right now, uh, as your IDS1 is equal to IDS2, sorry, this is IST2, so let me just use the mod. Now what we have to do is we have to find uh, the current. One second. Yep. Find the value of R4 such that the same current flow in the. Okay, we did the analysis using that same current flows, and now we have to find the value of R4. So this will involve this IR3 will be equivalent to IR4. So we'll assume a zero current flows through. So this will give me VDD minus VG2 divided by R3 is equivalent to VG2 minus V0 divided by R4, right? VDD is 12 volt minus VG2 is 10, R3 is 60K, R3 is 60K, and R4 is R4 we had to calculate 60K, and then again this is 10 volt minus V0 is 7.2 R4, right? That's 2 by 60K to R4 is equivalent to 2.8. So my R4 will be 2 point, this is 1.4 into 60K, right? My R4 will be 84 kilo ohm. Right? So this is how you find the value of distance. Next is we have to find gain. That's doing already. Let's look at the circuit. V in is here, right? And your V out is here. So how you can find this value? Easiest way will be this is V in here, R1 parallel R2. And the easiest way will be if you find directly the resistance looking into this terminal, the drain terminal of PMOS, right? Let's just let me just draw the circuit. This is again same analysis. You can use this as an assignment. Okay, okay. So this is your circuit. Let me just draw equivalent circuit here. So this will be R1 parallel R2. Union. Let's assume uh, no current flows through here, so it will be R3 parallel R4, and channel length modulation is given, so this will be R naught 1, right? And you will have another component here that will be related to resistance looking into, sorry, this is a RM2, right? RM2. Can you find this RM2? What you have to do is, this is your PMOS, this is your VX, IX, GM, VSG2. You just use this analysis, you find the value of RM2, and then it is a simple formula. Then to the gain of GM1, this is R01 parallel to R3 parallel R4 parallel RM2. This is how you will get your gain. Sorry, this is not in series. This has to be R4 only. Not actually R4, it should be R3 plus R4. right? What is the value of R3? R4 we calculated with, okay, 84 kilo ohm, right? So do this as an exercise, and if you have any questions, you can always ask. To find RO1 and RO2, just use this formula. This you have already calculated. This is your current. That is your 1 milliampere. You can easily find RO1 and RO2 because lambda are also given. Okay. So this, I suppose, is last question for the session. We had to find input capacitance. So I guess CGS should be given, CGS and CGT given. So my input capacitance will be CG, C input will be CGS plus CGT 1 minus gain, right? And C, this is given to us 10 and 5 pico. So my C in will be equal to 10 picofarad plus 5 picofarad 1 minus. What about gain? Gain you will have calculated in previous step. So if you happen to solve this question, you will find that gain is equivalent to 27. This is AV1 minus 50, right? So 150 picofarad, right? Okay, so if you happen to watch the video, please do check the answers and solve the questions on your own as well. If you have any questions, you can ask in the comment section. Let's just end this session over here. And let's meet next time.